Hi, this is Involved Innovation YouTube channel. In this video, we'll see about how one computer can communicate to other computer in the computer network. The most common standard for communication is TCP/IP protocol suite. The TCP/IP stands for Transmission Control Protocol. Why we need TCP/IP protocol? We will see with the analogy. If two people need to communicate, first they need to make sure they know some language in common. Person 1 and person 2 need to agree on a common language before starting the communication. If person 1 and person 2 does not have a known common language, then they might need to use an interpreter or communication cannot happen. The same applies to the computer communication as well. This communication happens through the network. Here the language is synonymous to protocol. These protocols define the format of data packets and the exchange process between devices. They specify details like header information, which includes source and destination addresses, error detection codes, control information, and other fields. That helps in successful data transmission irrespective of hardware, operating systems, etc. TCP/IP suite is communication protocol which is the foundation of internet communication. Let's take two devices want to send and receive data between them. It all starts with the sender network interface card. Each computer has a network interface card installed. This network interface card allows the computer to connect to the network and communicate with other devices. NICs can be integrated into motherboard or added as expansion cards. The data can be anything like image or video or Word document of any size. Let's take we need to transfer 1 GB of video file from sender computer to receiver computer. Here the data size is huge, so it cannot be transferred as a single piece. So this needs to be split into multiple smaller chunk packets of data. Since the data are split into multiple packets, we need to guarantee the order of packets for the receiver to reassemble, and what if one packet is lost and modified in the transmission. In the real world, there are so many computers. Like in physical world, every person need a from and to address. Here it is sender and receiver IP address and the information to uniquely identify the hardware systems, which are MAC addresses. These are only some of the requirements involved in successful data transmission. In real language, protocol is analogous to the grammar. This is what TCP/IP protocol suite provides, a guideline to follow for successful data transmission. TCP/IP protocol is a suite of communication protocol. It has 5 layers. All the communication protocol suite are based on the OSI model. The OSI stands for Open Systems Communication, and it is a conceptual framework for understanding how network communication should work. OSI model defines 7 layers that data traverses, each with specific functions like packaging, addressing, error checking, and so on. OSI is not a practical implementation but provides a standardized way on defining network communication to achieve interoperability between different systems. TCP/IP was originally developed by US Department of Defense. The protocols are defined in the RFC document is called Request for Comments document. The original TCP/IP documented on 1989 had 4 layers. It combined the application, presentation, session layer in the OSI model into a single application layer. Instead of network layer in OSI, it is called internet layer in TCP/IP model. The data link and the physical layer from the OSI model is merged to link layer in the TCP/IP model. This model was updated in 2005. In the latest TCP/IP model, there are 2 modifications compared to the original TCP/IP model. The internet layer in the original TCP/IP model is renamed to network layer in the updated TCP/IP layer, same like what we had in OSI model. Then the link layer is split into 2 layers as data link and physical layer like OSI model. So there are 5 layers in the updated TCP/IP model. Each performs a specific operation. Each layer wraps the contents it received from its immediate top layer with its own header. We will see how the message gets encapsulated when it travels from top to the bottom layer. Each layer has a different protocol for different purpose. For example, application layer supports HTTP for web request, SMTP for email, FTP for transferring the files, etc. We will cover these protocols in detail in another video. Now we will see how the HTTP request is converted in different layers. Here we will start with the HTTP request by opening the website wispath.com in the browser. This is the application layer, which is the topmost layer in the TCP/IP protocol suite. Application layer creates the message with the information such as HTTP version, HTTP method, here it is get, hostname wispath.com, and application layer also adds necessary headers to the HTTP message. These headers contain metadata about the message such as the content type, content length, cache directives, and more. If necessary, the application layer may also encode data in the message body according to the content encoding specifications, and the application layer may handle session management, maintaining state information between multiple requests for the same client. Now we have this data created in the application layer. This message will be passed to the transport layer, which is immediately below the application layer. This is the layer where the TCP and the UDP protocol comes in. This layer adds the TCP header on top of the data created in the application layer. Here we are using HTTP request, so for this it uses the TCP protocol. The TCP header contains various information. One of the key pieces of information is the source and the destination port. Port number is used to track the session. For the HTTP request, the default port number on the server is 80, and it can pick a random port on the source system per session. This is the reason we can able to access different pages of the same website on different tabs in the same browser. Let's take if we are requesting the about page in the wispath.com website and from the first tab and the blog page of wispath.com from the other tab. Having multiple ports from the source helps the browser in handling the separate sessions for each tab. To ensure the data from the application layer does not exceed the maximum allowable size for transmission over the network, transport layer fragments the data into TCP segments to fit in the maximum allowable size. Each segment gets the TCP header. This layer also ensures the receiver can able to reassemble the fragmented segments and ensures error detection and correction in the segment sent. We will see the functions of transport layer in detail later in this video. Network layer, which is immediately below the transport layer, adds its own header to TCP segments. This layer uses the IP and ICMP protocol. IP is the primary protocol used in this layer. Here the data is called IP packet. IP packets encapsulate the data within the IP header, which adds addressing information such as source and destination IP addresses. This layer is responsible for routing packages between devices across interconnected networks. Further fragmentation can also happen in this network layer if the size of the TCP segment exceeds the maximum transmission unit. If the size of the TCP segment exceeds the maximum transmission unit MTU of the underlying system. This layer also has the ICMP protocol. The ICMP is a companion protocol to IP and used for diagnostic and error reporting purposes in IP networks. ICMP is not used for general data transmission but rather for network management and troubleshooting tasks. Here the IP header also contains other fields including the source and the destination IP addresses. We will see the functions of network layer in detail later in this video. Data link layer, which is immediately below the network layer, gets the IP packet from the network layer. The data link layer encapsulates the network layer IP packet into frames, which includes headers, trailers for framing, and error detection. It provides mechanism for identifying the beginning and end of frames to delineate data boundaries. Data link layer translates network layer source and IP addresses into physical MAC addresses using the protocols like Address Resolution Protocol, ARP in IPv4, and Neighbor Discovery Protocol NDP in IPv6. Data link layer adapts the protocol specification to the characteristics of the underlying physical medium, such as encoding schemes, signaling methods, transmission rates. Different data link layer protocols may be used depending on the type of physical medium, such as Ethernet for wired connections or Wi-Fi for wireless connections. Other protocols include point-to-point protocol, high-level data link protocol, asynchronous transfer mode protocol, etc. The physical layer is responsible for converting the digital data into signals suitable for transmission over the physical medium and vice versa. This involves processes such as modulation, that is converting the digital data into analog signals. For example, the digital data 10111011, which is a binary data, will be converted to analog data based on the medium. If the medium is LAN cable, then it is electrical signal, or if the medium is optical fiber, then it is light signal. If the medium is wireless, then it is radio signal. The physical layer defines the characteristics of the physical medium, including transmission rates, signal voltages, cable types, connectors, and other parameters required for successful data transmission. Here, the medium is Ethernet, so the signal is electrical. So these electric signals are sent to the receiver system. Now we'll see what happens at the receiver end. Electrical signals sent by the sender physical medium reaches the receiver's physical medium. Here, the physical layer performs the demodulation, that is, converting the analog electrical signal to digital signal. Here, the digital signal is a binary code. Then the message reaches the network layer, which assembles the fragmented IP packets. We will see how the fragmentation and assembly happens in the data link layer in detail shortly. It allows checks for the errors in the IP packets. If there are errors, then it will ask for retransmission of that particular IP packet. Then the assembled IP packet reaches the transport layer where the TCP segments are assembled. Then the data is sent to the application layer where the receiver gets the request and constructs the response. The response contains the response code, other headers with the data. Then the data gets converted in each lower level, like what happened in the sender system. This process repeats. This is how two systems communicate in computer network. Now we will see the functions of each layer in detail. The main function of the transport layer are three-way handshake to establish connection between the sender and the receiver, ordered data transmission, retransmission of lost data, discarding duplicate packets during transmission, error-free data transmission, flow control and buffer management. First we will start with the three-way handshake. TCP three-way handshake is a method used in the transmission control protocol to establish a connection between two devices over an IP network. It involves three steps. First, the sender who wants to establish the communication with the server, example google.com, initiates by sending a TCP segment with a sync flag set. Sync flag indicates to the server that the client wants to initiate a connection. Here the key information to note in the TCP header are sequence number, which is a random value chosen by the client to start the sequence numbers for subsequent data segments. The acknowledgement number is not set. Upon receiving this TCP segment, server or the receiver creates a TCP segment with sync and acknowledgement flag set. This is the second step in the three-way handshake. Server also chooses its own initial sequence number for the connection and acknowledges the sender TCP packet by adding 1 to the sender's sequence number and sends this value in the acknowledgement number. For example, here the sender sequence number is 23424. Receiver or the server adds 1 to the sequence number, which is 23425, and adds this to the acknowledgement number. Sender, upon receiving the sender's sync acknowledgement segment, acknowledge with TCP segment with the acknowledgement flag set. Here the sequence number is increments of 1, that is the sender's first TCP segment sequence number is 23424. Now this TCP packet sequence number is 23425. And the acknowledgement number is server's sequence number incremented by 1, which is 43254. The server receives this acknowledgement and completes the three-way handshake. Now the connection is established. Both client and the server can begin exchanging data. This three-way handshake also serves as the mechanism to protect against sync flood attack, a type of denial of service attack where the attacker floods a server with sync segments to overwhelm its resources. By requiring the completion of three-way handshake, server can verify that incoming connection requests are legitimate and not part of an attack. TCP layer also guarantees the ordered data transfer of TCP segments. The TCP segment sent by the sender or the server can arrive in out of order. The order of the TCP segment is important to reassemble the data. Here the sequence number is used to order the TCP packet. We already saw in the three-way handshake, which allows both client and server synchronize the sequence number. For example, if the sender sends two packets with the sequence number 23426 and 23427, already the server knows this client's sequence number during the three-way handshake, where the client sends two TCP packet. For sync, it send TCP segment with the sequence number 23424, and for acknowledgement it send the sequence number 23425. So the server knows the next sequence number is 23426. So if the packet with the sequence number 23427 arrives before 23426, then the server TCP orders this TCP segments based on the sequence number. TCP also performs retransmission of lost data. TCP sets a timeout period for each segment it sends. This timeout period varies dynamically based on network conditions and the round trip time of the connection. If an acknowledgement of a segment is not received within the timeout period, TCP assumes that the segment was lost and triggers a retransmission. For example, here the sender sending two TCP segments with the sequence number 23426 and 23427 respectively. The sender set timeout for both these segments, and let's take the TCP segment with the sequence number 23426 lost in the transmission. Only the TCP segment with the sequence number 23427 received by the receiver. The receiver sends the acknowledgement for the TCP segment 23427 by adding 1 to the sequence number and sends this as the acknowledgement number to the sender. Sender receives this acknowledgement for the packet 23427 but not received acknowledgement for the segment 23426. So the sender resends this TCP segment 23426 again. TCP also discards the duplicate TCP segment if there are duplicates of TCP segment sent to the receiver. The TCP in the receiver discards those duplicate TCP segments. In the last example, we saw TCP in the sender resends the TCP packet if an acknowledgement for the segment is not received within a timeout period. This may introduce duplicate packet being sent to the receiver if the acknowledgement is delayed. Here the duplicate is identified by the receiver TCP by noting duplicate in the TCP segment sequence number. One of the important functions of the transport layer is facilitating error detection or error-free data transfer for the TCP segments. Before sending data, sender's TCP calculate a checksum based on the contents of the segment, including the header and the payload. This checksum is added to the TCP header. Upon receiving this segment, the checksum is recalculated by the sender and compared. If they don't match, it indicates the error have occurred during transmission. For example, there are two TCP packets which sender wants to send to the receiver. The sender calculates the checksum based on the TCP header and the body. The first segment checksum is 10110. The second segment checksum is 10010. This checksum is added to the TCP header and these segments are sent to the receiver. The receiver calculates the checksum of the received TCP segments. First segment it calculates as 10110. It verifies with the checksum in the TCP header. It is not matching. That means this TCP segment got corrupted in the transmission. So the receiver TCP discards this message and asks for retransmission of the TCP segment. TCP uses a sliding window mechanism for flow control. Each sender and receiver maintain a window size that indicates how much data can be sent or received before requiring acknowledgement. During the TCP three-way handshake, the sender and the receiver agrees on a window size. For example, during the first step in the three-way handshake, the sender sends the window size as 65535. The receiver acknowledges this with sync acknowledgement TCP segment and sends the window size as 32768 in the sync acknowledgement TCP segment. The receiver gets this TCP segment, finds out the window size of the sender is lower than what it sent in the sync TCP segment. So the maximum window size is the lower value between the sender and the receiver, which is 32768. Let's assume 8 segment can fit in the negotiated window size. So the sender sends 8 TCP packet without it need to receive the acknowledgement. While the communication proceeds, if the sender's data transmission rate exceeds the receiver's ability to process data, The receiver can throttle the sender by advertising a smaller window size. That is, sender can send a reduced window size as 2, 3, 4 to 5. That means sender can send only 6 packets without receiving acknowledgement. Now we will see about the different functions of network layer. The main purpose of the network layer is logical addressing. The source and the destination IP addresses are added to the IP header. The network layer also fragments the IP packets to smaller fragments to fit the maximum transmission unit size of the underlying network technology. Each network technology such as Ethernet, Wi-Fi or ATM has its own maximum packet size that it can transmit without fragmentation. IP packets larger than the MTU of a particular network need to be fragmented before transmission. The MTU will differ based on the underlying transmission medium. For example, if the IP packet size is 4500 bytes, which is greater than the Ethernet maximum transmission unit 1500 bytes, then the IP packet is split into 3 IP packets and the IP packet header is added to the fragmented IP packets. All these fragments get the same identification number to identify this all belongs to the same IP packet, and the offset field indicates the position of each fragment in the original packet. Here the first packet starts with offset 0, second fragment gets the offset 185 which is 1480 bytes divided by 8. The third fragment gets the offset 370 which is 2960 bytes divided by 8. Here the do not fragment bit is set, indicating that the sender doesn't want these fragments to be further fragmented by the other layers. The more fragments, when this bit is set to 1, then it indicates that there are more fragments to follow. It is set on all fragment except for the last one. Here this field is set for first 2 fragments and not set in the last fragment. When fragments arrive at the destination node, the IP layer examines their header to determine how to reassemble them. Fragments are reassembled based on information in their header, such as identification field, offset, and more fragments or do not fragments flag. This identification field helps the destination node match fragments belonging to the same original packet, while the offset field indicates the position of each fragment in the original packet. Once all the fragments belonging to the same original packet have arrived, the destination node reassembles them in the correct order to reconstruct the original packet. The receiver groups all the fragments belongs to the original packet with the help of identification number and assembles it based on the offset. Fragment with offset 0 starts as the first, next fragment with the offset 185, then the fragment with offset 370. The receiver checks the more fragment flag in each fragment. If it is unset, then that ensures this fragment marks the end of the fragment in the original packet. Here, this is unset in the last fragment, that means this is the last fragment for the original packet. Next we will see how the routing is performed in the network layer. This is one of the very important functions of the network layer. The network layer determines the optimal path for data packets from source to destination through a process called routing. Let's take we have 4 subnets. First, we will see a refresher on subnet. A subnet, short for subnetwork, is a logical subdivision of an IP network. Subnets are created by dividing a larger network into smaller, more manageable segments. Each subnet is identified by a unique network address and is associated with the subnet mask that defines the range of the IP addresses allocated to the subnet. A subnet mask is a 32-bit number used in conjunction with the IP address to divide the IP address into a network and host portions. The leftmost contiguous bits are set to 1 to represent the network portion, and the remaining bits to the right are set to 0 to represent the host portion. Here the network address is 192.168.3.0, and if the subnet mask is 255.255.255.0, then the IP range for the device in this subnet is from 198.168.3.0 to 198.168.3.255. Now we will go back to routing in the network layer. We have 4 subnets. Each subnet has specific CIDR range, and a device in the subnet's IP address will be in the CIDR range. To make this simple, we will consider each subnet connected to other subnet with the help of router. Router has 3 layers such as network, data link and physical. Here, as the initial step, each router gets the details of its neighbor's router and stores it in routing table. Example, R1 gets the details from all its immediate neighbor routes, that is R2, R4 and R3. The details include the destination IP, the router's IP as a gateway, column and subnet mask column, and then flag column to provide the additional information about the route. For example, U to denote this route is active and operational, G to denote that route uses a gateway, that is a next hop router. Metric column represents the route's metric or cost. Lower metric value routes are preferred because that increases transmission speed. Reference column specifies the number of references to that route. Use column specifies the number of times the route has been used. iFace column specifies the network interface associated with the route. Now we will see how the network layer sends the packet from the sender to receiver. Here the sender IP is 192.168.2.8 and the receiver IP is 192.168.3.6. The packet for the sender is sent to the router R2. It checks its routing table for the destination IP. The destination IP is not in the same subnet. As per the routing table, the packet needs to reach the router 1 to reach the destination IP. So, the packet is sent to the router 1. Here the router 1 checks the routing table for the destination IP address of this packet. The destination is not present in this subnet also, so the router R1 sends this packet to the router R3. The router R3 checks the destination IP of this packet in its routing table. It finds this IP address is present in this subnet because the gateway field in the routing table for this entry is 0.0.0.0. The packet is now sent to the destination IP 192.168.3.6. This is how the routing happens at the network layer. Now we will see about the functions of the data link layer. The primary function of the data link layer is it encapsulates network layer packets into frames, adding necessary control information such as headers and trailers. The data link layer adds the physical MAC address of the source and destination to frames to identify the source and the destination devices on the local network. Here the source and destination system are present in the same network. The sender with the IP 192.168.1.10 want to communicate with the receiver with the IP 192.168.1.12. Sender knows the receiver IP address but not the MAC address. The MAC address is the ID associated to the network interface card. Sender checks its ARP cache for the receiver MAC address. If it is present, then that is added to the destination MAC address. Here it is not present, then the sender generates an ARP request packet containing its own IP and MAC addresses and the IP address of the receiver. Sender broadcasts this ARP request onto the local network. Receiver, upon receiving the ARP request broadcast, checks if the request is for its IP address. Recognizing its IP address in the ARP request, then the receiver generates the ARP reply as a response packet containing its own IP address, MAC address, fulfilling the request from sender. Receiver sends this packet directly to the sender. Sender, upon receiving the ARP reply, it updates its ARP cache, associating the receiver's IP address with its MAC address. Then the MAC address is added to the frame and the data is sent to the receiver. Here the sender and the receiver are in the same local network. What if the sender and receiver are not in the same local network? Let's see that with an example. Here the sender IP address is 192.168.1.10 and the receiver IP address is 203.0.113.5. The sender, same like before, creates an ARP request packet with its MAC address and IP address and receiver's IP address. Sender broadcasts this ARP request onto all the machines in the local network. Since the receiver is not within the local network, none of the devices within the local network can respond to the ARP request. The ARP request packet reaches the default gateway, which is the nearest router. The router recognizes that receiver is not within the local network and needs to forward the packet to another network. Here the router engages in proxy ARP. it replies to sender's ARP request with its own MAC address, pretending it to be the receiver. This response tricks sender into sending packets intended for receiver to the router. The router receives packets destined for receiver from sender and forwards them towards the network where the receiver receives. Now the router sends out ARP request on receiver's network to obtain its MAC address. Receiver, upon receiving this request, responds with the ARP response packet with its own MAC address, and this reaches router. Once the router knows receiver's MAC address, it will update the frame it received from the sender with the receiver's MAC address and forward the frame to receiver successfully. The data link layer also performs collision detection with CSMA CD, which is carrier sense multiple access with collision detection protocol, which is used in Ethernet to regulate access to the shared transmission medium and handle collisions when they occur. The sender listens to the network to check if the transmission medium, that is the Ethernet cable, is idle. If it senses the medium is busy, that is another device is using the same transmission medium Ethernet cable, it waits for a random backup time before attempting to transmit. If the medium becomes idle after backup, sender starts to send the data. While transmitting, the sender continues to monitor the network. If it detects that another device is transmitting at the same time, then this results in the collision. It stops transmitting immediately. After detecting a collision, the sender sends jam signal to inform other devices regarding the collision. The jam signal is a predefined sequence of bits that alerts other devices to stop transmitting and wait for a random backup time. The sender waits for a random backup time before attempting to retransmit. The backup time is typically chosen to reduce the likelihood of another collision. During this backup time, the sender continues to listen to the network to ensure it remains idle. After the backup time elapses, if the medium is ideal, the sender retransmits the data. In this video, we have seen the complete TCP/IP protocol set. Thanks for watching this video. For more technical videos, subscribe to this channel. If you like this content, like this video, share it with your friends. Thanks for watching.